All right, so last class. Last class we talked about, we started off by reviewing residual analysis. So residual analysis in the context of ANOVA is our method for finding or for validating the normality assumption and for validating the constant variance assumption. The other two assumptions, independent populations and simple random sample, that would just come from experimental design knowledge. So we can't empirically verify those. After we reviewed the residual analysis material, we started to talk about contrasts. Now, as a reminder, a contrast is a linear combination of means. So in the illustrations that we are looking at, in the illustration that we are looking at, we have 4 population means that are available to us, which means that we can consider all different types of comparisons between those population means. For example, in part C, we are taking the average of the first 2 means and comparing that to the average of the second 2 means. So we have the contrast, which is shown here, which is equal to 1/2 mu1 plus 1/2 mu2 minus 1/2 mu3 minus 1/2 mu4. Okay, so this is a contrast that compares the average of mu1 and mu2 to the average of mu3 and mu4. Now, what can we do with a contrast? Well, we can build confidence intervals and we can construct hypothesis tests. So just like we learned in the 2 sample inferential case, in the 1 sample inferential case, and even for the ANOVA, we can conduct statistical inference about this population quantity. Now, our inferential approaches are going to be very, very similar to what we saw before. The only differences are that the formula that we utilize to compute the interval and to compute the test statistic of the hypothesis test are going to change to accommodate what we call the pooled variance procedure, or the pooled variance estimate, and the coefficients of the contrast. So for example, on slide 8, this is our formula for computing a confidence interval for the population contrast of interest. On slide 9, we have the steps of the associated hypothesis tests for the contrast. And you can see that the hypotheses for the contrast here have the same, or we have the same 3 types of null and alternative hypothesis that we had when we introduced hypothesis testing at the beginning of the course. All right, so we started working through an illustration based off of the 3rd contrast from part C that we looked at last class. So just as a refresher, we're working with the minke whale data. So we're measuring the body length of the whales. We have 4 treatment means, and we are interested in part A. In part A, it reads, researchers are interested in determining if there is evidence that the average length of the whales between depths of 0 and 99 is different from the lengths of the whales between depths of 100 and 199 at the 5% significance level, right? So we're just constructing a hypothesis test for the difference between the average of the first 2 means and the average of the second 2 means. So in part A, our contrast, which we derived in part C of the first problem in the lecture set, is gamma equals, and I should have said, I don't know if I specified this, but this is gamma. So gamma is equal to mu1 plus mu2 over 2 minus mu3 plus mu4 over 2. So we have coefficients C1 equals C2 is equal to 1/2, and C3 equals C4 is equal to -1/2. So this hypothesis test would have null and alternative hypothesis, gamma equals 0 versus gamma not equal to 0. So this is the same idea that we saw before. We want to know if there is a difference between mu1 and mu2 and mu3 and mu4. So a difference between the averages of the first two means and the second two means. Okay, so we want to know if there's a difference, so we use a two-tailed does not equal test. And then you can see that by setting gamma equal to 0, what you end up with is a direct comparison of the average of mu1 and mu2 to the average of mu3 and mu4. On step 2, we have alpha 0.05, and then on step 3, we have the computation of the test statistic. Now, in computing the test statistic, we actually found the solution to part B. So part B of this problem asks us to find the standard error of the contrast. So the standard error of the contrast is this part here, which is given here. Okay. So this is the solution to B. All right, now at this point, we have to just finish off the test, right? Okay, so to finish off the test, we just do exactly what we always do. We either can run the p-value approach or we can run the critical value approach. So on step 4 here, just for illustrative purposes, I'm just going to run through the p-value approach, but you can verify the result using the critical value. So if we take the p-value approach, we have our t-curve centered at 0. We have a test statistic of negative 5.399. So here is t equals negative 5.39. Actually, it would be 5.4 because if we round to 3 decimal places, we have to round up. It's a two-tailed test. So on the other side, you have t is equal to 5.400. All right, so our p-value is going to be the area in each tail. All right, so our p-value is equal to 2 times the probability that t exceeds 5.400. The degrees of freedom for our p-value is equal to DFE from the ANOVA table. So this is the only real switch that when we're building a confidence interval or conducting a hypothesis test about a contrast, we use the degree of freedom error from the ANOVA table. So our DFE is going to be, I believe it was 101 minus 3, 101 minus 4, which is 97. I'll just have to check that really quick here. So the DFE from the ANOVA table was 90. Why did I do it this way? So long. There it is. Okay, so the DFE from the ANOVA table for the minke whale experiment was 97. Right. Okay, so we are going to have a t-value here with degree of freedom equal to 97. So again, once we get to the p-value critical value step, the process is exactly the same. It's just that we're using information from the preceding ANOVA to finish off the test. So the ANOVA will always come first before a contrast. All right, so if we go to our t table now, we have 97 degrees of freedom. Sorry, I just need to load the t table. So we're going to be on page 2 of our t table. Okay, so we have 97 degrees of freedom. So we have 95 and 100 on the table. You always round down when using DF. So we round to 97. We have a significance level of 0.05, or actually, sorry, that doesn't matter. So we round down to 95. Our test statistic is 5.40. Okay, so we are larger than the largest listed value on the line. So our p-value is therefore less than 0.005 in each tail. Right? Okay, so then we can say since probability t greater than 5.400 is less than 0.005, then the p-value is less than 0.01, since we have to multiply by 2 because it's a two-tailed test. All right, and then following from that, we can reject the null. So we're just saying that there's evidence that the average of mu1 and mu2 is different from the average of mu3 and mu4 in this case. Okay. I'll just fit that in over here. So so any questions about the hypothesis tests or any general questions at all?
Does that say reject the null hypothesis or the alternative? Because it kind of looks like an A.
So we always make our conclusion about the null. So it would be reject H0. Okay, so part B, just as a reminder, part A says give the null and alternative and estimate the standard deviation. Sorry, so this is not the solution to part B. This is just the standard deviation. So that's our part A, and this is going to be solution to part A. Sorry about that. Okay, part B. So part B says, for the test in A test statistic of negative 5.40 was found. What is the result of this test? Hint, perform step 5 and step 6 of the corresponding hypothesis test. Okay, so part B, it actually starts here, right? So we want to find the result of the test about the comparison of the averages of mu1 and mu2 and mu3 and mu4. So the result of the hypothesis test of interest is going to be found using either a critical value or a p-value approach. So I've demonstrated the p-value approach here, but you can easily confirm this using the critical value approach because it's just a critical value for a two-tailed t-test on 97 degrees of freedom, right? So we've seen many examples of this up to this point. So as I had mentioned, we're going to reject the null here because our p-value is less than alpha. So the conclusion to the test would be at the 5% significance level, the data provide sufficient evidence to suggest that the average value of the minke whale lengths between 0 to 99 meters is different from the average minke whale length between 100 to 199 meters. So I have written here, at the 5% significance level, the data provides sufficient evidence to suggest that the average value of the minke whale lengths between 0 to 99 meters is different from the average minke whale length between 100 to 199 meters. So that's what we found evidence of. The null hypothesis said the average of 0 to 99 was equal to the average length of whales trapped from 100 to 199. The alternative was that the average length of whales between 0 and 99 is different from the average length of whales between 100 and 199, which in terms of our population means was mu1 plus mu2 over 2 equals mu3 plus mu4 over 2 versus the alternative that those quantities are different. We rejected the null, and by rejecting the null, we then have evidence that the population means are different from one another, which means that we have evidence that the length of the whales trapped between 0 and 99 is different from the length of the whales trapped between 100 and 199. Does anyone have any questions? All right, so part C says, will a 95% confidence interval have negative bounds, positive bounds, or one negative, one positive bounds? Explain. Okay, so let's think about what's happened here. We have conducted a two-tailed hypothesis test at the 5% significance level. So first thing that we have to think about is the critical value for this hypothesis test going to be the same as the critical value for the 95% confidence interval? So yes or no, what do you guys think? Any ideas? Okay, so the answer to that question would be okay, well, the answer to the question would be yes, right? Does anyone have an idea why that would be the case? Am I getting trolled right now? Are you guys still here? Yes, for what? So the question that we're looking at is part C. Will a 95% confidence interval have negative bounds, positive bounds, or one negative, one positive bound? So we have looked at a two-tailed hypothesis test at the 5% significance level. So are the critical values for that hypothesis test and for the confidence interval going to be the same? Yes or no? And the answer to that question is yes. I'm wondering if anyone follows that logic or could say why. Okay. Well, under the assumption that you guys aren't sure, so we have the following null and alternative, and we tested at alpha 0.05. Therefore, sorry.
So it shouldn't, it would not contain 0.
Yes, that's correct. So would the bounds be negative or positive?
Positive?
They'd be negative. So I'll show you what. So we have, just for clarity, so on step 4 of the hypothesis test, our t value would have been t alpha over 2 on DFE, which is t 0.025 on 97. If we built a 95% confidence interval, on step 1, the t value would have been exactly the same. So it would have been t alpha over 2 DFE, which is t 0.025 on 97. Okay, so same critical value in HT and in CI. Therefore, the results will agree. Okay, so that's the first part. So the first thing I just wanted to do is, or we need to do, is just make a recognition that our two-tailed hypothesis test at the 5% significance level will have the same critical value as the confidence interval at the 95% level. And we've seen examples of this in the two sample procedures as well, but the same logic is going to follow even for the contrasts and the comparisons. So we have the same critical value. That just means that the results are going to be exactly the same. So in B, we rejected H0, which means that we have evidence that mu1 plus mu2 over 2 is not equal to mu3 plus mu4 over 2. Okay, so we have found evidence that there is a difference between the average of mu1 and mu2 and the average of mu3 and mu4. So the 95% CI will not contain 0. Okay, which is the correct answer that was given. Now the question is, will the CI be a plus and a plus, a negative and a negative, or negative plus? Okay, it can't be negative plus because it doesn't contain 0. So if the bounds were going to be a lower bound negative and an upper bound positive, that would have to contain 0 because numbers run from negative to positive. Okay, so this one is automatically out. We know that the interval either has to have 2 positive bounds or 2 negative bounds. How do we determine which? Okay, so the answer, the bounds on interval will match the sign of the sample contrast / test statistic. So if you think about this in terms of what we have already calculated, our sample contrast for the problem is negative 2.19, and our test statistic is negative 5.4. We know that the interval cannot cross 0. So if the interval can't cross 0, but the midpoint of the interval is going to be a negative number, then the interval has to have 2 negative bounds as well. Because otherwise, you have to cross 0 in order for the upper bound to get into the positive numbers. Okay, so for part C, the first thing that we do is identify whether or not it will contain 0. If it contains 0, you're going to have a negative bound and a positive bound. If it does not contain 0, then the signs of the bounds on the interval will match the sign of the test statistic / the sample contrast. So here, therefore, the interval will have two positive bounds. Any questions about that idea?
Wait, I thought you just said it was negative.
Oh yeah, sorry. Thank you. Good catch, good catch. Any other questions / clarifications? All right, so what is the practical use of a contrast? So we have seen examples of contrasts for comparing collections of means, right? So we just looked at an illustration where we took the average of two means and compared it to the average of another two means. We also saw setup examples where we took the average of three means and compared it to one mean directly. When we conduct an ANOVA, if the ANOVA gives evidence to reject the null hypothesis, that means that we have found evidence that there is a difference among a set of two means. So for example, in the minke whale experiment, there are 4 different treatment means. The ANOVA null hypothesis could be rejected if mu1 and mu2 were significantly different from each other, or if say mu2 and mu4 were significantly different from each other. You could have within the context of rejection of the null, all possible pairwise combinations being different, or you could have just one pair of means being different. So the natural question that falls out after or comes out of rejection of the ANOVA null hypothesis is, where does the difference lie? So what two means are actually different from each other? So is mu1 different from mu2? Or is mu1 different from mu4? Or is mu2 different from mu4, etc.? So our technique for determining where the difference lies is done through what we call computing all pairwise combinations. And more specifically, what I should say is done by considering all pairwise combinations and through the technique that we call multiple comparisons. So a multiple comparison is simply refers to the process of comparing all possible means within an experiment to one another. So for a data set with K treatment groups or with K population means, okay, so this would be the same thing as saying K population means. There are K choose 2 different possible pairwise comparisons. Okay, and that's just our combination rule. Not something we really need to focus on, but just to emphasize the point, that the more population means you have in an experiment, the more pairwise comparisons you have to consider. When we perform a multiple comparison of all possible treatment means, we have to adjust the value of alpha within each comparison. So you might recall from our discussion in lecture set 2 that alpha is also the probability of type 1 error. The probability of type 1 error is something that we want to control across the entire experiment. So suppose that you have to perform k choose 2 multiple comparisons. And suppose that k is a number like 5 or 6. So you have somewhere like in roughly like, let's say 30 different comparisons to control. If you let alpha equal 0.05 for each individual comparison, there is a compounding effect where the overall experimental error would be larger than 0.05. So to control this, we specify what is called an experiment-wise alpha, and this would be the alpha for the entire set of pairwise comparisons. And from that value, we then compute the individual type 1 error. So we call that alpha subscript I. So that's the alpha value for each multiple comparison. So alpha subscript E is alpha, the significance level for the entire set of pairwise comparisons. And alpha subscript I is the significance level or the alpha value for each individual comparison. Okay, now in order to find the value of alpha I, you first set alpha E. So alpha subscript E, which is our experiment-wise significance level, we declare that. And this value usually matches what is given from the ANOVA. So if our ANOVA is conducted at the 5% significance level, our alpha subscript E is going to be 0.05. If the ANOVA is conducted at the 1% significance level, our alpha subscript E will be 0.01. To find the value of alpha subscript I, there are a number of different procedures that could be utilized. So for example, on the slide, I've listed 4: Tukey HSD, Tukey Kramer, the Sheffe, and then the Bonferroni. The Bonferroni is the approach that we're going to focus on in this lecture set, and it has a very simple adjustment to alpha subscript E to give us the alpha subscript I. So the way the Bonferroni multiple comparison would run is as follows. Declare alpha subscript E. Okay, again, whatever we use for the ANOVA, we're going to use as our alpha subscript E. Compute the number of pairwise comparisons you have to make. Again, this value here, which we call little m, this is simply k choose 2, which is k choose 2. Right? So this is something you can compute very directly using any scientific calculator. This is just the combination rule being applied to the number of treatment means, and you want to pick 2. Basically, what you're asking is how many different ways can I compare 2 things from a set of k things? To calculate the alpha subscript I, which is what this alpha star is here, so this is alpha subscript I, you take alpha subscript E, and you divide that by 2 times m. So again, it's a very simple idea for controlling overall type 1 error. So we declare our experiment-wise error rate, which is the significance level from the ANOVA. We calculate the number of pairwise comparisons that we have to make. That's k choose 2. And then we take the experiment-wise error or the experiment-wise significance level and divide that number by 2 times m. And then this alpha I value becomes the value you plug in for each pairwise comparison of the mean. Okay, now In the Bonferroni procedure, on steps 4, 5, and 6, we have a specific way of approaching the problem. But the reality of the situation is this. Suppose that you have 4 means and you want to determine all possible pairwise comparisons that you have to perform. So I have 4 treatment means, 4 choose 2 is 6. So I have 6 different comparisons to perform in order to determine where the differences lie. And again, I should mention that the only reason we would do a multiple comparison is if we reject the null hypothesis of the ANOVA. So if we run an ANOVA and we do not reject the null, we don't have to perform multiple comparisons because the ANOVA has already given us evidence that the means are equal. So there's no purpose in searching for differences if we have evidence that all means are equal. So we're only going to run the multiple comparison if we reject the null hypothesis in the ANOVA. The way that a multiple comparison works is you take each pairwise comparison and you basically run a 2-sample t-test about the pairwise comparison, or you build a confidence interval about the pairwise comparison of interest. So basically, we follow up an ANOVA with a set of hypothesis tests and a set of multiple comparisons. Now through SPSS, this process is very easy because SPSS will spit out all of this output for you, and it'll give you p-values and confidence intervals for every single comparison. So this can be done very quickly. When we are doing this by hand, we develop ways to try and simplify the process. So one way that we can do this is only by computing the margin of error for each of the different comparisons. And by then only computing the margin of error for each comparison, computing the difference between the means of interest, and then checking to see if the margin of error is bigger or smaller than the difference. Another way you could do this is just to construct all the 95% CIs directly. But in the name of trying to be efficient, again, our usual strategy is compute difference between the means, compute margin of error for every difference, and then check to see if the margin of error is smaller than the difference. Because if it is, this would mean that the 95% CI will not cross 0. But I'll show you an example of that as well. But in summary, multiple comparisons are just sets of hypothesis tests or confidence intervals. When we do it by hand, we take the confidence interval components because it's a bit faster to work through the comparison using those components. Okay, so for the minke whale data set, we have the 4 population means. When we ran the ANOVA on the minke whale data, we found evidence that suggests that there is evidence of a difference among that set of 4 means. So our question is now, where does the difference lie? So if we use the Bonferroni procedure, we start by declaring our overall significance level. So we have alpha E here. This is alpha from the ANOVA. Then we compute the number of comparisons here. So this is little m is 4 choose 2, which is 6. Then we compute alpha star. This is our alpha I. So this is 0.05 divided by 2 times 6, which is 0.0041. Okay, now at this stage, you might be wondering, okay, or you might be thinking, in SPSS, this is possible because we can compute any specific significance level and any specific p-value for any set of degree of freedom. But if I have to do this by hand, what would I do? The only real option, if you're running multiple comparisons by hand, is to round to the closest significance level. So here we have 0.00416. The t-table only gives us up to 0.005. So we would have to use the 0.005 the corresponding t-values at 0.005 to compute our confidence intervals / margins of error. It's the only real option in this case. Okay, now what we have to do is compute the margin of error for each different combination. So these 6 combinations here are going to be mu1 versus mu2, mu1 versus mu3, mu1 versus mu4, mu2 versus mu3, mu2 versus mu4, mu3 versus mu4. So those are the 6 combinations that we are interested in considering. So for the first comparison, which would be mu1 versus mu2, we compute the corresponding margin of error. So the margin of error is going to be the t-value on alpha star, comma, the DFE, multiplied by the square root of the MSE, multiplied by the square root of 1 over n1 plus 1 over n2. So you can see here that we have our t-value on this specific alpha star. We have the MSE from the ANOVA table, which was 0.9, and we're using the sample sizes from the first and the second group. Okay, what if we wanted to consider as a second option the margin of error for, I don't know, comparison 2, 3. So if we wanted to consider mu2 versus mu3, this is going to have the exact same t-value. It's going to have the exact same MSE. And then in this case, we're doing 2 versus 3. So we would have the following. So you can see that the only things that are changing in the multiple comparison are the sample sizes that are associated with the comparison. Yeah, it's always choose 2 because multiple comparisons are always can only be about 2 means because they're basically just 2 sample inferential procedures. So it's always going to be number of groups, choose 2, no matter what. Okay. Once we compute the margins of errors, we can construct them in a table like that given on step 5 here. Okay, so here I have a table of E. So this 0.703 here, this is just the value that I showed here. So each of these values in the table are just computed by using the margin of error formula. And the only difference between the values is the sample sizes that are associated with the comparison. So if we are working through a problem where every single group has the exact same sample size, we're going to have the exact same margin of error in all of our comparison slots. Then what we do is we build a table of absolute differences between the means. Okay, so for example here, I'll call this star 1. Right, so this is going to be the absolute value of 4.49 minus 5.06, which is equal to 0.57. This value here is going to be the absolute value of 4.49 minus 5.75, which is equal to 1.26. And then one more example, this value here, number 3, this is going to be 4.49 minus 5.99, which is equal to 1.50. Okay. And then it's the same process for all the other means. I mean, I might as well just show a couple more. Like if we do number 4 here, so this is this is going to be 5.06 minus 5.99. No, sorry. Yeah, 5.75. Sorry, minus 5.75, which is equal to 0.69. Now, the last thing to do is just say, before we get to the conclusion, so the question that we ask coming out of the tables, well, basically, no, let's not call it a question. To complete it, we'll call this the rule. So the rule for finding differences. If E is less than x bar I minus x bar j, then difference exists. So basically all we have to do now is compare the absolute difference to the margin of error. So for example, 0.5, well here, let's highlight it over here. Okay. 0.703 is bigger than 0.57, therefore no difference. Okay, and then if we go mu1 versus mu3, we would say 0.633 is less than 1.26, therefore difference. Okay. So we're just taking the margin of error and comparing it to the corresponding difference in means. If the margin of error is smaller than the difference in means, that gives evidence of a difference. If the margin of error is bigger than the difference in means, that means that there's no difference. Okay. So here we would have 0.796 is smaller than 1.50, therefore difference. Here we would have mu2 minus mu3. So 0.748 is bigger than 0.69, therefore no diff. And then we can continue that for the last two. Okay, so then in the end, we can conclude at the 5% significance level, the data provides sufficient evidence to conclude that a difference exists between the average body length of the whales entangled at depths of 0 to 49 and 100 to 149, right? So this is mu 1, mu 4, 0 to 49 and 150 to 199. Sorry, this is mu 3. This is mu 1, mu 3, and 50 to 99 and 150 to 199. So that's mu 2, mu 4. Okay. So our multiple comparison is telling us that mu 1 is different from mu 3. Mu 1 is different from mu 4. And mu 2 is different from mu 4. All right. So I'm going to stop there because we're basically out of time, but does anyone have any questions at this point? Yeah, sorry. Good catch. Thank you. Any other questions or concerns or corrections? Oh, no, that's good. Yeah, I'm glad that you caught it. No need to apologize. Okay, well, as always, if you guys have any questions, please let me know. So we have the lab assignment number 2 due on Monday, and then the assignment 3 lecture is due next Friday, and then we have reading week. So we'll continue. So we're going to start lecture set 6 on Monday, which is on randomized block designs. And that it'll be material for the assignment 4 and lab assignment 3 probably. Okay, so yeah, as always, if you guys have any questions, please let me know. If not, I will talk to you Monday at 1 p.m.